All right. So you should have your cards kind of sorted out here. Okay. Now, the first thing that I want to talk about are the particles that we discussed yesterday. So yesterday in the video, they showed an unstable nuclei that sneezed. And when it sneezed, it emitted particles. And so the particles that can be emitted are a alpha particle, a beta particle, and a gamma particle. And if it is an alpha particle, it is like a 4-2, so it's like a helium nucleus, okay? And if it is a beta particle, it's like an electron. And if it's a gamma particle, it's a photon of light. Jordan, your papers are over there by the colored pencils. Okay, so take a look at the particles of helium, right? All right. So when I look at the particles, what I'm looking at are, I got to kind of identify which particle is which. And if you remember from your notes yesterday, gentlemen, I'm not talking over you. So you just won't be in a group together. If you look at your notes from yesterday, you will see that a gamma particle is the biggest and the clunkiest, and it causes the least damage. It can be stopped by a sheet of paper. A beta particle can be stopped by a piece of aluminum foil, right? It has a little bit more energy, but not much. And the gamma rays are where all the damage is really at, because the gamma rays are stopped by concrete, okay? So they're the most powerful, and it's like a photon of light. Okay. Now, we're going to do a little bit of, why isn't this working? So now we're going to do a little bit of decay practice. So the first card that I want you to take out is K42. Okay. Now, on yesterday when we did this practice, right, we used this kind of format. And so this number, this top number, is the mass number. This is made up with protons and neutrons. This bottom number is the atomic number. That's just protons. Okay? And if you notice, it says it beta decays. Now, yesterday, when we saw that there was something that was going to beta decay, we used the word emit. And so now, what symbol is represented with emit? An arrow. So now put your arrow in. So now you may have to kind of stand up to get all this put together. Okay? And then it's going to emit a beta particle. Well, what is a beta particle? Which one is your beta particle? Yep. Carter's holding it up. It's 0 minus 1 E. I know you're on your phone, so put it away. And by away, I mean in your backpack, because people don't stare longingly at their crotch. Well, some people do, but that's uncomfortable. Okay? Now, when you have the beta decay that happens right here, then you put a plus symbol. And then you do the math. Now remember, my clue here is you always add. So 42 plus 0 is 42. And then 19 plus 1 is 20. So find your card, because what you should have in front of you would look like this: 0, 1, A, right? And then the math would be 42, 20, calcium. Now, the whole point of radioactive decay is that things that are unstable are getting rid of particles, alpha, beta, gamma particles, in order to become stable. So I can actually calculate if something is stable. And the way that I do that is I'm going to take the mass number, which is 42, and subtract 20 from it, because this number right here is the number of protons. And in order for something to be stable, there needs to be a 1-to-1 ratio of protons to neutrons. So if I take 42 minus 20, I get 22, which means there are 20 protons and 22 neutrons. Now, the ideal ratio is 1-to-1. Is 20 to 22 a 1-to-1 ratio? It's not, but it's pretty close. So this is actually stable. Okay, let's go to the next one, the decay scheme practice. Get your Li6 out. Now you're probably going to have to take these cards apart because you're going to be able to use them all. Now notice that your Li6 card, it's going to alpha decay. So if you take a look on the screen, this is my unstable parent. Then it's going to emit, so I've got an arrow, an alpha particle. The alpha particle is going to be that 4,2 helium. And then I got to do the math. So 6 minus 4 is 2. 3 minus 2 is 1. And what's the element that I'm dealing with? Hydrogen. So you should have this represented on your desk. Now, we got to figure out if it's stable. How do I do that? Mass minus the number. 2 minus 1 is 1. So now this tells me the number of neutrons. This number tells me the number of protons. When I compare these two, is it a 1-to-1 ratio? Yes, which means because it's a 1-to-1 ratio, this is stable. I'm telling you that the ideal ratio is 1-to-1. This is pretty close to 1-to-1, okay? So it doesn't have to be exact, but if it is, then you know it's absolutely stable, okay? Get out your next card. So the next decay one is going to be Pu 239. And notice that it alpha decays. Okay. So now, if you take a look up here, you've got Pu 239. Now, you should all have periodic tables on your desk. Okay. What is the atomic number of Pu? 94. Okay. And according to this, it's going to alpha decay. So set up your alpha decay. So it's going to look like this. And then we're going to do the math. 239 minus 4 is 235. 94 minus 2 is 92. And it is uranium. So that's my first daughter. Okay. Now, I want to figure out if this is stable. What do I have to do? 235 minus 92. That gives me 3. Is it 4? 143. Okay. Now I'm going to compare these numbers. 92 to 143. Is that a 1-to-1 ratio? No, and it's not even really close. So this is unstable, which means it's probably going to still do some decaying. Okay. Go to your next one. Oh, PA 229. And it's going to undergo 2 consecutive alpha decays. Now, some of you are going to try and do all the decays consecutively, meaning you're going to alpha decay, and then you're going to come up with an answer. You can't do that. You can't do that because you're eliminating a daughter then. We got to have both daughters. So it should look like this. What's 89? What's 89? AC. What's this one? 87. Francium. Okay. Hey, I am so glad that you guys are having a good time in science today. I am super glad. But half of you haven't completed the assignment because you're piddle farting around talking to each other. Here's what you should have. Here is your daughter. Then you alpha decay it again. Here is your next daughter. Okay. Now go to polonium 210. Okay. So the next one you want to go to is polonium 210. And if you see, it's got an alpha-alpha, beta-alpha decay. Now, in class, we're just working with note cards, and they're putting the note cards together. You could write this out on your sheet so that you know what you're doing, okay? So when I'm looking at this, I have a helium, and anytime I have my alpha particle here, I have to subtract 4 from the amount. So I'm going to have 206, 82. This number is the atomic number. So I'm going to look on a periodic table and I'm going to look for the atomic number of 82, and I find that it is lead. And then there's another alpha decay, and that's a 4,2 helium particle. So I take 206 minus 4, and I get 202. And then 82 minus 2, and that's 80. This number is my atomic number, so I have to look it up when I see it is Hg, or mercury. That's my second daughter, okay? Now there's a beta decay. Well, with beta particles, you're always going to add. So now you say to yourself, 202 plus 0 is 202. And then plus 1 is 81. And then what's that going to give me? Well, I'm looking for 81 on the periodic table, and it looks like TL, thallium. Now that's the third daughter, but it's still not done decaying. So it decays this alpha particle, and what it does is 202 minus 2, or minus 4, is going to be 198. And then 81 minus 2 is going to be 79. I'm going to look this up on the periodic table. It's AU. AU. Okay, so the next thing that we're going to do is do what's called a hypothetical decay scheme. Now, you should have this paper if you were in class on Monday, but if you weren't in class on Monday, you're probably just going to have to use your own piece of paper. So here's what you're going to do. You're going to get a penny or whatever, a quarter, doesn't even matter, and you are going to flip it, and you're going to create a hypothetical decay scheme. And so every time you flip a heads, it's going to be an alpha particle, and every time you flip a tails, it's going to be a beta particle. So I'm going to start with my unstable parent. This is my unstable parent, and it is going to, I'm going to flip my coin, and it is going to emit a beta particle. So now here I'm going to do the math. So it's going to be 238. So 238 plus 0 is 238. And then 92 plus 1 is going to be 93. And I have to look this number up on the periodic table to see that it's NP. Now this is my daughter. So I'm going to start my next generation with my daughter. 238, 93, NP. Now I'm going to flip my penny, and it's going to flip heads. And that's an alpha particle. So that's going to give me a 4,2 alpha particle. Now I'm going to do the math. 238 minus 4 is 234. And then I'm going to subtract 2, which is going to be 91. And that element at 91 is PA. That's my second daughter. That daughter is going to start the next generation. So it's 234, 91, PA. Now I'm going to flip my penny. It's going to be a beta decay. I'm going to do the math. 234, 92. That's uranium. This is my third daughter. So now I'm going to start here, 234, 92, U, and I'm going to keep flipping pennies until you get all the way down here. Then when you get to number 15, I need to know if it's stable or unstable. How am I going to know if it's stable or unstable? You take this number minus this number. So whatever you end up with, you take the mass minus the number, and you get a number here. This is the number of protons compared to the number of neutrons. If it is a 1-to-1 ratio, like 20 to 20, then that means it's stable. If it's not a 1-to-1, then it's not stable. If you get that done, then you're caught up for the day in science. There will be an assignment. It's going to be thorium 232. And you might have to just do that in class when you get here.